The universe is dark. Not night sky dark, not the kind of darkness where stars still glitter like silver nails through velvet. This is deeper, quieter, a darkness without witness. Every star that ever burned has cooled into a black dwarf. Every supernova has faded, every galaxy has gone dim and silent. Space hangs cold and endless, a cemetery of extinguished suns drifting forever through a sky that remembers nothing. And yet, you and I were born in the age of fire, to stand in this moment, the universe after its final light. We have to walk backwards across trillions of years. We have to imagine the violence that once illuminated everything, hypergiants so vast they could swallow our solar system whole, magnetars whose magnetic fields could tear matter apart, neutron stars spinning faster than the blades of any machine humans will ever build. There were stars you could see from across half a galaxy, and others so small and dim that their light never reached us. Every one of them lived by the same fragile rule. Fusion pushing outward, gravity crushing inward, a tightrope of fire stretched across cosmic time. But even fire has an end. The last star flickers, fades, and leaves the universe in true night. No warmth, no sunrise, no blue-white glow across the edge of a planet. Just the long exhale of creation, the final silence after the orchestra has finished its last note. And this is where our story begins. Not with how stars are born, but with what happens when the universe runs out of light, and how that journey, from brilliance to dark, eventually became you. Before we follow those echoes back through time, before we peel open the night to find the first sparks of starlight struggling into existence, I want to offer something gently. If stories like this make you feel small in the best possible way, if cosmic wonder calms you like deep breath after a long day, I would be truly honored if you would consider subscribing. If this journey stirs something quiet in you, even a little, a like or comment helps others find their way here too. One curious mind, one resting heart at a time. No rush, no obligation, just a small shared moment in a universe too large for anyone to walk alone. Now, let's reverse the dark. Let's trace the last stars backward to the explosions that forged the iron in our blood, to the nebulae that cradled young suns like embers, to the moment light first broke open the void. And everything began. Start with a monster that rewrites scale. Canis majoris is a red hypergiant so swollen with heat and time that if you set it where our sun sits, its surface would extend beyond the path of Jupiter. A single day on its photosphere would feel slow and ghostly. Convection cells rise and fall like continents, each one large enough to swallow Earth 1,000 times over. The outer layers boil and shed in arcs, forming dusty knots that drift and fade. Light needs hours to cross from one side of the star to the other, so even its own surface cannot respond in unison. It breathes in flares and outflows, shaping a nebula from its own loss, a star so vast that its edges blur into the medium between stars. Every metric collapses into understatement near it. Its radius dwarfs imagination, its luminosity drowns any notion of a normal day. Here, astronomy feels like weather on an alien world. Now snap the scale the other way. Take more than a sun's mass and squeeze it into a sphere barely wider than a city. A magnetar is that contradiction, dense enough that a teaspoon would outweigh mountains, compact enough that gravity locks atoms into a lattice of neutrons, and yet wild with magnetism. The field is so intense that it distorts electron shells and stirs vacuum into action. Magnetic lines twist and snap, and when they do, the star rings like steel, releasing bursts that carry more energy than most stars emit in years. Everything near a magnetar must submit. Molecules unspool, matter rearranges, and radiation storms wash through space like silent lightning. The quiet of interstellar distance offers no safety. Their reach is not in gravity or wind, but in raw electromagnetic force, cutting across light years with no warning. We learned how far that reach extends in late 2004. A magnetar catalogued as SGR 1806-20, sitting about 50,000 light-years away, fired a flare so sharp it rattled Earth's magnetic field after crossing the galaxy. It arrived as a brief spike, a flash of gamma rays saturating detectors built to watch violent skies. The source then faded in a tail of ringing pulses as the star rotated, as if the crust had cracked and the magnetic field snapped into a new shape. Satellites glitched. The ionosphere responded. For a fraction of a second, the magnetar rivaled the brightness of the full moon in high-energy light across a distance that swallows every human timeline. We didn't go looking for it. It found us anyway and left a note written in radiation that said, "Dead stars are not done." Not every neutron star keeps its anger in sporadic flares. Some spin with metronome precision. Pulsars sweep beams through space like lighthouses, and the fastest ones twirl hundreds of times per second. At 700 rotations each second, the crust strains against centrifugal forces that would explode any ordinary object. Only gravity this intense can keep the star intact, fusing protons and electrons into neutrons until the matter itself becomes a quantum crowd. The surface is a sheet of nuclei packed into a crystalline solid, the interior a soup of neutrons with superfluid behavior where friction barely exists. That physics makes the spin steady enough to rival atomic clocks, until starquakes shift the crust and the rhythm jumps. Astronomers time those beats to microseconds and map the cosmos with their regularity. A teaspoon from that star would weigh billions of tons. A mountain there could be centimeters tall. Even the word mountain fails. These extremes do not stay put. Some stars are thrown out of their homes and sent toward the emptiest places we know. Runaway stars form when gravitational tides snap a bond in a crowded cluster, or when a supermassive black hole plays slingshot with a binary, or when a companion explodes and the survivor keeps its speed. Their trajectories end not at the edge of a spiral arm, but beyond the faint glow of any galaxy. Kick a star to a few million miles per hour, and it can outrun the pull of its birthplace, lofting into the dark between island universes. There, time stretches into silence. The star will age with no neighbors, no companions, no recycled gas to drift into, no nearby explosions to enrich any future worlds. It will exhaust its fuel and dim alone, its story written where no one reads it. This exile is not rare. The galaxy sheds stars the way a campfire sheds sparks, each one bright and brief against the larger night. Follow one of these exiles back to origin, and you often find violence. A compact object lurking in the center of a galaxy can tear a binary apart and fling one star away with escape velocity while swallowing the other. Dense clusters host close calls where three body dances redistribute energy and eject a partner. Even the quiet death of a massive star can unbind a system. The sudden loss of mass in the explosion changes the gravitational balance, and the companion flies on. Hypervelocity stars carry chemical fingerprints of their youth and scars of their launch, like peculiar rotations or stretched orbits frozen into straight lines. They cross the halo, pass through sparse clouds, and feel the weak pull of the Milky Way fade. If they survive long enough, they will leave even the local group, and the darkness will not return them. All of this makes one humble ball of light feel different. Our sun, average in mass and in age, sits comfortably away from the center and far from violent clusters. It turns once every 4 weeks, not hundreds of times per second. It holds stable at a size that lets planets form and keep orbits for billions of years. It throws off flares that can trouble a power grid, not sterilize atmospheres across light years. When weighed against hypergiants and magnetars, it looks tame. But that calm is not an accident. It is the consequence of mass placed neatly in a narrow range where fusion proceeds at a measured pace, and gravity asks for only what fusion can provide. In a universe that builds monsters by default, a stable middleweight is the oddity. The thread tying these fates together is mass. Give a star more mass, and gravity pushes harder, forcing the core to run hotter. The nuclear furnace speeds up, radiation floods outward, the envelope expands, and the star burns through its fuel at a wasteful rate. It shines like a city of suns and dies young. In a few million years, shedding layers and exploding, leaving behind either a neutron star or a black hole. Give a star less mass, and its core never reaches those extremes. Fusion proceeds slowly, mixed by convection that sips hydrogen with care. It glows red and cool, and it can outlast galaxies. Mass sets the clock, selects the color, determines the temperament, and writes the epilogue. At the top end, mass creates instability at every level. In the atmosphere, gigantic convective cells lift plasma into arcs and loops that drain energy and momentum. In the core, rapid fusion builds heavier elements layer by layer until energy gains stall with iron. The star then finds no more profit in fusion. Gravity no longer meets a sufficient push, and collapse begins. Milliseconds later, a shock wave blasts outward, and the core squeezes into a neutron star. If the core is heavy enough, even neutrons cannot resist, and the horizon closes into a black hole. At the low end, the physics turns thrifty. Red dwarfs stay mixed, so they use almost all their hydrogen. They cool slowly and never swell into the wild extremes of a hypergiant. The line between star and not star appears below them in brown dwarfs, where mass falls short of sustaining fusion and the glow is leftover heat that fades. Between those ends, magnetism, rotation, and environment add texture. A star born in a dense cluster might gather companions and end in a chaotic ballet. One born in relative solitude drifts on a quiet orbit and ages in place. Rotation amplifies magnetic fields, drives winds, and sculpts mass loss. Magnetic fields, in turn, alter how energy escapes and change how a star breathes over time. Nearby massive stars can strip a neighbor's envelope with ultraviolet radiation and accelerate its evolution. Accretion from a companion can revive a dim core and trigger new outbursts. Each star lives its own conditional story, but all of them obey the simple script set by mass at birth. So the hypergiant at one extreme and the magnetar at the other are not contradictions. They are endpoints on a scale that begins with the same ingredient. The cosmos does not choose spectacle for its own sake. It lays down matter and lets gravity and fusion sort it out. The larger stars rush toward explosive endings. The smallest settle into persistence. And in that quiet middle, our sun's balance looks improbable, even lucky. A steady flame in a theater that prefers catastrophes. The question that follows is simple and unnerving. What keeps that balance at all, and why does it fail so differently across the spectrum? All the chaos we've just met rests on one plain rule. Strip away the fireworks and the exotic leftovers, and a star is a standoff. Gravity tries to pull every atom inward. Fusion pushes outward with heat and light. A star exists only while those two forces are equal to a fine margin. That delicate tie is called hydrostatic equilibrium, and it holds not by chance, but because the core produces just enough energy to support the weight above it. When that energy generation shifts, the balance shifts, and the whole star responds. Think of it as the simplest equation in the sky. The inward side is the star's own mass. The outward side is pressure born from nuclear reactions in the core. If the core lags, layers settle and squeeze it harder. That extra squeeze raises temperature and pressure, which speeds up fusion and boosts the push. If the core runs hot, the star swells, the gas relaxes, and fusion eases back. The result is a self-correcting system until fuel runs low or transport of energy changes. Then the regulation starts to falter, and the path forward bends toward a new state. That balance is not forgiving. A small lead for fusion makes the outer layers expand and cool. The star bloats into a subgiant or giant. A small win for gravity makes the core contract. Heat spikes, opacity changes, and instability can grow. When the core can't find a new fuel to take over, collapse accelerates. In large stars, that final winning blow comes fast because gravity scales with mass and pressure gradients steepen. In smaller stars, the system adjusts slowly, buying immense time at modest power. Down where the light is born, hydrogen nuclei meet. In stars with masses like the Sun or less, the dominant engine is the proton-proton chain. Protons tunnel through their mutual repulsion, bind, and step through reactions that end with helium-4, positrons, and neutrinos. Each step releases energy that becomes heat and radiation, and that energy is the outward force that holds the star up. In heavier, hotter cores, another route dominates: the CNO cycle. Carbon, nitrogen, and oxygen serve as intermediaries, speeding fusion at higher temperatures. Either way, a tiny bit of mass is converted to energy, according to E equals mc squared. And that tiny bit is enough to light a world from across space. But starlight does not burst straight to the surface. The core is so dense that photons scatter incessantly. A single gamma-ray photon is absorbed and re-emitted countless times, changing direction with each interaction. This random walk turns a direct path into a long diffusion. The timescale is not measured in minutes, but in tens of thousands to millions of years, depending on the star's structure. Most of the interior is a radiative maze. Higher up, where temperature falls and atoms can hold electrons, opacity rises and makes radiation less efficient. There, large cells of plasma rise and sink. Convection takes over, hauling energy like slow, boiling weather. Only at the photosphere, the thin layer where the gas becomes transparent enough, does light stream freely into space in a straight shot. The color of that escaping light is a straightforward thermometer. Hotter surfaces emit more blue and ultraviolet, cooler ones more red and infrared. That is the basis of spectral classification. O and B types at the hot end, then A, F, G, K, down to M at the cool end. Our sun sits in the G range. The hue tells more than temperature. It hints at lifespan. The hottest, bluest stars burn bright and fast because their cores require much higher pressures and temperatures to hold off gravity, which drives furious fusion rates. The coolest red dwarfs sip fuel slowly. Their interiors are often convective from core to surface, mixing fresh hydrogen into the center and stretching their lives to durations that make galaxies seem young. Journeying outward layer by layer, a star's anatomy follows function. The core is the furnace. Wrapped around it is the radiative zone, where energy leaks outward as photons scatter through ionized plasma. Above that sits the convection zone, an ocean of rising hot gas and sinking cool gas that shapes granules and supergranules on the surface. The photosphere is the visible surface, a few hundred kilometers thick, where light finally escapes. Beyond it, the chromosphere adds a thin veil of hotter, rarer gas. Then comes the odd part, the corona. The corona defies simple expectation. It is much thinner than the lower layers, but its temperature runs into the millions of degrees, far hotter than the photosphere beneath it. This coronal heating problem points to magnetic processes, twisting field lines, reconnection events, and waves that dump energy into the outer atmosphere. The link between magnetism and heat is under active study, and missions designed to race close to our star were built to probe these processes and capture the physics that traditional remote sensing cannot resolve. The takeaway is sober. Even the star we know best keeps back key details about how it moves energy and shapes its environment. Mass ties all these pieces together. With more mass, gravity presses harder, That pressure demands higher core temperatures to maintain balance. Higher core temperatures mean faster fusion. Faster fusion means a brighter star, but a shorter life, because the fuel is spent quickly. This mass luminosity rule shows up across the main sequence, and it sets the stage for how each star leaves it. The giants that begin life with massive cores cannot climb far before iron or the lack of pressure support ends the game. The smallest stars never face such extreme cores. They simply keep fusing hydrogen until long after familiar galaxies change form. Equilibrium is dynamic, not static. As hydrogen converts to helium, the mean particle count in the core falls, the pressure support per unit temperature changes, and the core contracts to raise its temperature enough to sustain the outward push. That contraction shifts where energy is made, alters the opacity, and transforms the interior transport. A once fully radiative star can grow a convection zone. A once shallow convective layer can deepen. In time, the center becomes pure helium. If the star is heavy enough, helium fusion will ignite and build carbon and oxygen. If not, the core stalls and the outer layers respond by swelling into a giant as the shell around the core fuses hydrogen at a furious rate. Meanwhile, a photon born in a core with different composition faces a changed landscape. In a radiative interior, its random walk depends on how easily ions and electrons absorb and scatter it. As elements build, the opacity mix shifts. In a convective zone, parcels of gas carry heat outward. Those parcels overshoot, cool, and sink. The surface brightness patterns that telescopes resolve trace those convective cells. This churning is also tied to magnetic fields. Rotation and convection work together to wind magnetic loops that break, reconnect, and launch streams of energetic particles. Color, again, reads destiny in plain sight. A red dwarf's cool surface points to a low-mass interior that keeps its fuel mixed. That gives it a near-immortal main sequence compared to the age of the universe. A blue giant's glare tells on itself a huge mass, a searing core, a pace of fusion so high that its clock runs fast. When balance falters in such a star, the change is not gradual for long. Shells of burning stack up, hydrogen outside, helium inside, then heavier elements if mass allows, until the chain stops at iron, where fusion no longer pays the pressure bill. The sun's place in this scheme is quiet, but precise. It holds balance by steady hydrogen fusion, supported by a radiative interior and a convective outer layer. It turns plasma flows into a magnetic cycle that modulates activity on its surface and in its wind. Over time, the slow drift of helium ash in the core will raise temperature and brightness. The photosphere will grow hotter and the star more luminous, nudging climates of any nearby worlds and setting distant conditions for later change. The thread is simple, but rich. Mass sets gravity's demand. Temperature and pressure in the core set fusion's supply. Energy finds its way outward by diffusion and by moving gas, and the final surface lets light run free. The outer atmosphere stores magnetic stress and releases it as heat and storms. All of it together makes a star stable for a while and then steers it off that balance when the fuel mix evolves. That evolving mix is the hinge. No star stands still, even in its calmest phase. The equilibrium shifts with composition, with structure, and with the way energy climbs from the heart to the skin. That shift is the trigger for the next act in a star's life, when steady output gives way to swelling layers, pulsing brightness, and new fuels lighting up in deeper shells. The contest between gravity and fusion never stops. It only changes form, guiding each star toward a specific ending written by its mass and by how long its core can keep paying the pressure debt. Start with the quiet workhorses. A small red dwarf sips fuel so slowly that it can shine for 1 trillion years. It mixes its core and envelope, keeps hydrogen available, and wastes almost nothing. In another corner of the HR landscape, a blue giant races through its life in a few million years. It pours energy outward with such intensity that its surface runs blisteringly hot and its core changes composition rapidly. Two philosophies of existence, one thrift, one extravagance. Both obey the same physics, but mass steers the timetable and sets the tone. Most stars live their longest stretch on what astronomers call the main sequence. During this phase, gravity pulls inward while fusion pushes outward with equal strength, and the star holds a stable shape. Hydrogen converts to helium in the core. The energy released marches outward and escapes as light. This equilibrium lasts for billions of years for stars like our Sun. For larger stars, the balance holds for a much shorter span because their higher core temperatures drive faster fusion. For smaller ones, low core temperatures throttle the reaction and extend lifetimes to spans that exceed the universe's current age. That stability misleads. A star on the main sequence looks steady, but internal changes never stop. As hydrogen fuses into helium, the core's makeup shifts. Helium does not fuse at the same temperature and pressure as hydrogen. The core contracts slightly, heats up, and the fusion rate increases. That, in turn, makes the star brighter over time. The star you see today is not quite the same star it was eons ago. The changes hide beneath a calm surface, but the clock is moving. Our Sun offers a good anchor for time. It has kept a steady rhythm since dinosaurs walked Earth. Across human history, it has barely budged in temperature or brightness. It will remain on this plateau long after our species is gone. Yet even the Sun drifts upward in luminosity very slowly as the core composition evolves. Billions of years from now, that gradual rise will matter to climate and habitability in our solar system. On stellar timescales, a small shift compounds into a large consequence. The Hertzsprung-Russell diagram lays out this landscape in a single plane. Temperature along one axis, luminosity along the other. Blue-hot stars cluster on the upper left, brilliant and rare. Mid-range yellow stars, including the Sun, sit along the center sequence where balance holds for eons. Down in the lower right, red dwarfs gather in huge numbers, faint and cool. Their abundance means they dominate the census of stars, even though each one contributes little light. The diagram is not just a chart, it is a map of life paths. Where a star sits hints at how it formed, how it burns, and how it will end. As a star's core hydrogen drops, the center contracts and heats. The outer layers respond by swelling. A star that once kept a compact shape expands into a subgiant and then a giant. The surface cools somewhat even as total energy output rises because a larger surface area spreads the heat. Meanwhile, the core temperature continues to climb until helium can fuse. When helium ignition begins, the core settles for a while into another balance, but it does not last like the main sequence. Each new fuel comes with new rules. Massive stars go further because their cores reach the conditions needed for heavier elements. After helium, carbon forms. With higher temperatures, oxygen follows, then neon, magnesium, and silicon in layered shells. Each stage happens faster than the last. Carbon burning might last thousands of years in a very massive star. Oxygen hundreds, silicon only days. The chain stops at iron. Fusion of iron does not release energy. It absorbs it. At that point, the star's engine loses the ability to support the core against gravity by fusion alone. What follows depends on mass, but the iron limit marks a turning point that no massive star can ignore. Not all stability is steady. Some stars pulse. Cepheid variables and their cousins like RR Lyrae stars regularly brighten and dim as their outer layers expand and contract. The mechanism ties to how their envelopes trap and release heat, setting up rhythmic changes in pressure. These cycles can be precise, and the tempo correlates with true brightness. That relationship turns them into yardsticks. By measuring the period of pulsation and the apparent brightness, astronomers can calculate distance. In that sense, a heartbeat becomes a ruler that spans vast space. Even stars that never pulse on human timescales still move through phases. Hydrogen depletion nudges that internal balance away from perfect match. The core contracts, heat builds, shells of fusion ignite at different radii, and the star swells. The main sequence ends not with an abrupt cut, but with a drawn-out shift. Over time, the structure becomes layered like an onion, with different elements fusing in stacked zones. The complexity grows until the star's mass dictates the final scenario. Red dwarfs, due to their deep convective envelopes, stir their interiors top to bottom. They burn nearly all of their hydrogen rather than only the core portion, making them extraordinarily efficient. They lack the mass to move into helium burning for a long time, so their lives stretch out over inconceivable spans. Many will never even reach later phases within the lifetime of the universe as we know it. Blue giants, by contrast, run at high pressure and temperature, with radiation dominating energy transport in their interiors. That environment drives rapid core changes and shortens their lives dramatically. They pay for brilliance with time. The main sequence, then, is a long middle chapter, but it is not an endless plateau. As fuel dwindles, the same physics that once stabilized the star starts to push it toward change. Core contraction raises temperatures. Envelope expansion alters surface conditions. Energy transport modes can shift from radiative to convective or vice versa as gradients steepen or relax. Even a star that looks the same tonight as it did last year sits on gradients that are slowly moving. Consider how the sun's brightness has crept upward by a few percent over hundreds of millions of years. That small drift hints at larger changes to come. In the distant future, helium fusion will begin in the core under different conditions than hydrogen, and the outer layers will balloon outward. The familiar star that anchors our sky will become a giant, and the solar system will adjust, or fail to adjust, to that new regime. All of it follows from the same balance that governs the main sequence, inward pull against outward push. Cepheids remind us that even a stable structure can support oscillations when the conditions are right. Their predictable brightness cycles carry information across space. Our Lyrae stars, though less luminous, play a similar role in our own galaxy and its neighbors, marking the skeleton of old stellar populations. These variables do not just decorate the sky, they mark distances, ages, and histories, turning brightness changes into clues. As massive stars escalate to heavier fuels, the pace accelerates. Silicon fusion stacks iron in the core quickly. With no energy to be gained from fusing iron, gravity tightens its grip. For stars below that threshold, the swelling into giants and the ignition of helium set a gentler course. But even there, the main sequence is a one-way road. Hydrogen in the core is finite. The balance that seemed so steady will tip. So the calm phase we think of as a star's adult life masks a running negotiation. There is no true stasis, only a long series of near standstills as composition shifts. Red dwarfs lean toward patience, blue giants toward haste, the sun toward a comfortable middle. The HR diagram holds their positions like a snapshot, but time moves each point along a path set on the day the star formed. The path bends toward transformation. Hydrogen depletion ensures that gravity will gain leverage. Increased core temperatures and new fusion shells will reshape the star and prepare it for the finale that mass prescribes. The middle years lead naturally to disorder, bloated atmospheres, layered cores, and the beginnings of instability. From here, the story of stars loops back to crowded birthplaces where gravity gathers cold gas and, out of turbulence and shadow, the next generation's first light struggles into being. We've watched stars end in violence and settle into quiet embers. Now we step backward into a space with no light at all. The glow and color drop away. What remains is cold gas and dust, so thick with fine particles that visible light cannot get through. These are molecular clouds. They stretch for hundreds of light years, deep reservoirs of hydrogen with traces of helium and heavier elements. Through a telescope tuned to visible wavelengths, they look like gaps in the sky. With radio and infrared, they reveal depth, structure, and motion. Inside those dark volumes, gravity works in silence. A slight density increase here, a pressure wave there, and sections begin to sag inward. The cloud doesn't collapse as a single block. It fractures into clumps and cores. Each dense pocket tightens, and as it does, the gas heats. No starlight falls here, but temperature rises all the same because potential energy is turning into heat. The core thickens. Pressure grows. The collapse accelerates until friction and compression slow it, and the first hints of an internal balance begin to appear. This is the start of a protostar. It is not yet shining from fusion. It glows because it is hot from infall, wrapped in dust that re-radiates energy into longer wavelengths. Material streams inward through a rotating accretion disk. That disk feeds the center while also storing angular momentum. Rotation flattens the inflow into a plane, and the geometry shapes the next stage of growth. Around the young object, the dusty disk orders itself into rings and clumps where solids can stick, collide, and grow. The core continues to tighten as gravity deepens the well. Magnetic fields thread through the disk and the newborn star. As material falls in, the fields twist and channel energy out along the poles. The result is a pair of collimated jets, straight and fast, throwing gas back into the cloud. Those jets relieve the system of angular momentum, which in turn lets the core accept more mass. When the jets strike slower material nearby, they produce glowing knots and shock fronts. Cavities open where gas has been pushed aside. The cloud shows scars and hollows where young stars have started clearing their rooms. In a single giant cloud, thousands of these stories play out at once. Some clumps grow fast and become massive. Others stall. Some break in two, setting the seed for binary stars with tight or wide separations. Nearby giants flood the area with ultraviolet radiation. Their light eats away at exposed surfaces and evaporates small disks that stray too close. Winds from hot stars blow bubbles into the gas. At the edges of these bubbles, squeezed material can tip into collapse, triggering a fresh round of cores and protostars. It is a feedback loop. Heat and pressure oppose gravity at one spot and enable it at another. The Orion Nebula offers a clear view of this process. It lies about 1,344 light-years away within a larger system of clouds that spans much of the constellation. A cluster of young, massive stars there bathes the region in intense radiation. That light strips electrons from atoms, makes the gas glow, and sculpts pillars and walls. Infrared observations cut through the dust and show compact sources buried inside. Many of those sources are embedded protostars. Around them, disks mark the raw material of planets. The bright cavities and sharp edges record where radiation and winds have carved space clean. Growth in these nurseries is productive, but not perfect. Brown dwarfs appear throughout the fields. They form like stars do, but they do not gain enough mass to maintain hydrogen fusion in their cores. They cool with time and dim. Their existence signals the wide range of outcomes when gravity acts on cold gas. Some systems cross the threshold into sustained fusion. Others fall short. Still others will become planets once their host stars settle and their disks thin out. Crowding defines these birthplaces. The gravity of one young star tugs on its neighbors. Close passes can tilt or trim disks. Small bodies get scattered inward or outward. In dense clusters, a star can be nudged onto a path that will take it far from its siblings, turning it into a wanderer long before it reaches maturity. At the same time, many stars bind into pairs or groups. Their mutual pull will shape orbits and future evolution for billions of years. The initial tangle of motions sets conditions that persist long after the cloud dissipates. The raw material in these clouds is not pristine. Older stars supplied it. Winds from giants shed layers of carbon and oxygen into space. Explosions from massive stars sprayed iron and the other heavy elements. Over time, that debris mixed with hydrogen and helium and drifted into fresh clouds. When gravity gathered those clouds, the next generation inherited metals and dust. Those elements are key to cooling gas, forming solid grains and building planets. Birth owes a debt to previous deaths. As a protostar gains mass, its center grows hotter and denser. When the core reaches the necessary conditions, hydrogen fusion begins at a low rate. Pressure rises from within. Infall slows. The main sequence lies ahead, but the star is still encased in a dusty envelope and thick disk. Radiation pressure starts to push outward from the surface. The jets continue to punch channels through the environment. Over time, the young star clears a path. The surrounding cocoon thins. More light escapes. In some cases, a massive neighbor accelerates this clearing. Ultraviolet photons strike nearby disks and blast gas away, leaving tight, silhouetted shapes with tails pointing away from the source of radiation. These exposed disks, once carved, may lose volatile material faster and alter the types of planets that can form. In other areas, shielding allows disks to retain gas longer. The exact placement of a star within its nursery shapes its architectural options. The Orion region shows this variety at high resolution. Some disks lurk in shadowed lanes protected from the cluster's glare. Others sit at the edges of H2 regions and wear their photoevaporated rims openly. Cavities link to larger bubbles. Filaments trace where the densest gas channels mass toward growing cores. Across the complex, you can track ages from deeply embedded protostars to young stars already visible in optical light. The entire zone operates as a sequence, from dark inflow to cleared surroundings, all within a few dozen light years. Star formation also occurs on grander scales. When galaxies interact, gas can compress on kiloparsec fronts. That compression ignites waves of formation where clusters and superclusters of stars arise together. The rate climbs, the supply drains quickly, and the system spends its fuel on a brief storm of creation. On smaller scales, a single supernova's shock may squeeze a nearby clump enough to set it collapsing. In both cases, the same physics applies. Push the density high enough, let the gas cool, and gravity takes over. Not every collapse ends with a shining star. Some fragments dissipate before they reach critical density. Others get stripped by a neighbor's radiation or torn by tidal shears in the cluster's potential. Timing matters. Distance matters. The mass of the core matters most. Cross the threshold, and fusion will light. Fall short, and the object drifts into the long, slow cooling of a brown dwarf or a giant planet. As the young star brightens, it negotiates with its environment. Radiation pressure and stellar winds push outward. The envelope thins. The disk feeds the star and also loses mass to jets and heating. Eventually, enough material clears that starlight streams freely into space. The nursery begins to empty. The star steps out from its cradle. What remains of the disk now holds the seeds of asteroids, comets, and planets. Collisions and accretion continue for millions of years, but the phase of hidden growth is over. Every star that will later swell, collapse, or explode starts with this hidden work in the dark. It leaves the cloud altered by neighbors, sculpted by radiation, and equipped with a disk that sets the blueprint for its system. From here, its path will be set by mass and time. Radiation lifts the fog, and sends the newborn outward, away from the nest and toward the long arc where equilibrium changes, fuel runs down, and the return to darkness begins. Start with something close to home. Our sun will swell, not tomorrow, not in any human time frame, but it will happen. As hydrogen in the core runs down, the core tightens and heats, and the outer layers respond by spreading outward. Oceans will boil away as the heat ramps up long before the sun reaches its largest size. The atmosphere strips off, the crust bakes, and the quiet daytime star becomes a swollen red giant that fills much of our sky. It will not blow the solar system apart in a single blast. It will simply overtake the inner worlds as its surface cools and reddens while its reach grows. Stellar death is not one story. It is a range of endings governed by a single variable: how heavy the star was when it formed. Lower mass stars tend to fade quietly. Massive stars end with violent suddenness. The physics behind both endings lie in the same contest we already met: gravity versus fusion. As fuel dwindles, the balance tilts. How it tilts depends on mass and on the last fuels available at the core. When a star like the Sun runs short on hydrogen in the center, fusion there slows and gravity begins to pull ahead. The core contracts, raising the temperature until fusion switches to a shell around the core. That extra energy causes the outer layers to loosen and expand even as the surface cools. The same star that once held a narrow, stable radius becomes a red giant with a bloated atmosphere and a cooler outer glow. The paradox is common in stellar life: a shrinking, heating core paired with an expanding, cooling surface. Layers start to separate. Helium collects in the core. The envelope becomes unstable and can pulse, and with each pulse, the star sheds mass into space. Follow that gentler path to the end, and you get a planetary nebula. The name is historical and misleading. It has nothing to do with planets. The outer atmosphere drifts outward in glowing shells, lit from within by the exposed core. We see rings and eyes and halos, because different layers leave at different speeds and densities. The Helix Nebula shows a layered eye-like structure where gas expands into surrounding space. The Ring Nebula forms a luminous torus with delicate filaments and a faint halo. At the center sits the leftover core, a white dwarf the size of Earth with the mass of the Sun, supported not by heat but by quantum pressure of tightly packed electrons. It does not fuse. It glows from stored heat and cools very slowly. Over billions of years, it fades toward a state so dim and cold it becomes a theoretical black dwarf. Massive stars do not get that quiet ending. Their cores climb a ladder of fusion stages as conditions intensify. After hydrogen, helium fuses to carbon and oxygen. With enough mass, the core reaches temperatures where heavier elements build in sequence, up through silicon-producing iron. Iron marks a wall. Building iron does not yield energy. It costs energy. Once the core grows iron-rich, outward pressure from fusion can no longer keep up. Gravity takes control in a fraction of a second. The core collapses at tremendous speed. The outer layers plunge inward and then rebound off the suddenly stiffened core. A flood of neutrinos and the shock front drive the envelope outward in a supernova. For days, the dying star shines as bright as a galaxy. The explosion hurls newly formed elements into space at thousands of kilometers per second. What remains at the center depends on the mass that went in. Many cores stop collapsing when neutrons pack together and resist further compression. That creates a neutron star, only about 20 kilometers across, with gravity strong enough to hold matter at densities beyond atomic structure. Some neutron stars spin hundreds of times each second because conservation of angular momentum speeds up their rotation as they shrink. Their magnetic fields focus radiation into beams that sweep space like lighthouse signals. If the collapsing mass is higher still, even neutron pressure cannot hold it back. The core continues inward past the point where light can escape, forming a black hole with an event horizon defining a boundary of no return. We see supernova remains across our galaxy. One famous remnant still glows, the Crab Nebula. It expands outward as filaments of gas energized by a central pulsar, a rapidly rotating neutron star that powers the nebula's glow. The remnant records a star's death noted by observers in 1054 CE, while the object we see now is the aftermath of the same event, still pushing material into surrounding space. Stellar death seeds planets and people. Heavy elements do not come from the early universe's first moments. Hydrogen and helium dominated then. Stars built the rest. Smaller stars manufacture carbon and oxygen in their cores and release them in winds and gentle shedding. Massive stars forge elements up to iron while alive, and their explosive deaths create and scatter heavier nuclei into space. Those elements mix into gas clouds that later form new stars and planets. Iron in blood, calcium in bones, and gold in rings all trace back to stellar deaths before our solar system formed. The timeline is long. The process repeats. Each cycle boosts the heavy element content of star-forming clouds, making later planets richer in the materials chemistry needs for rock, water, and life. There is another path to supernova that begins not with a giant, but with a small leftover. A white dwarf can steal mass from a companion in a close binary. If it gains enough to reach a critical mass, conditions in the core trigger a runaway reaction. The star detonates in a Type Ia supernova. These explosions reach nearly the same peak brightness because they begin at a similar mass and composition. That consistency turns them into reliable distance markers. By comparing how bright a Type Ia supernova appears to how bright it should be, astronomers measure how far away it is. Using these standard candles revealed a surprise in how the universe grows. Distant Type Ia supernovae looked dimmer than expected for their distances, which means they are farther away than a simple constant expansion would predict. The conclusion is that the expansion of space speeds up. We give the cores a name, dark energy, but the mechanism remains unknown. The key here is that the death of stars gives us a tool to weigh the universe's history, to read the rate of expansion across time, and to trace the geometry of space on the largest scales we can test. Return to the quiet path and notice how long endings can be. A white dwarf may glow for billions of years as it cools. Its surface can show scars of a past life through carbon and oxygen lines in its spectrum. It can host a debris disk from shattered planets or asteroids perturbed by the shift in gravity during the giant phase. Some white dwarfs have atmospheres polluted by heavy elements, a sign they are accreting material from surrounding debris. For massive star remnants, the story continues with pulsar wind nebulae, expanding shells interacting with interstellar gas, and shock fronts that heat surrounding material to X-ray temperatures. These structures drive waves through space that compress nearby gas and encourage new star formation. Even in death, stars shape their environment. The spectrum of endings also includes borderline cases. Some stars hover near the limit between forming a neutron star and forming a black hole. Others shed so much mass through winds before collapse that their supernovae look stripped, lacking hydrogen in their spectra. In crowded regions, binary partners can alter each other's fates. A pair of massive stars can exchange material, changing which one explodes first and what remnant is left. A neutron star with a companion can later merge, releasing still more heavy elements and a distinct kilonova glow. Each path circles back to the same core idea. Initial mass and environment set the stage, but interactions and timing write the final script. Our sun will not end in a supernova. It will expel its outer layers and leave a white dwarf in the quiet center of an expanding nebula that fades over tens of thousands of years. Long after, the remnant will cool through a slow descent in temperature, drifting toward darkness. Elsewhere, heavier stars will continue to die with catastrophic force, lighting galaxies with brief, brilliant flares and throwing the building blocks of worlds into space. These deaths are not only endings, they set up the conditions for the next round of star formation and for the appearance of planets that can hold liquid water and complex chemistry. From that chemistry come cells, tissues, and thoughts. One star's final act becomes another world's beginning, and that chain links the sky's bright explosions to the quiet materials at your fingertips even now, as we turn toward how those deaths tie into the structure and history of everything beyond our galaxy. Start wide, and then step all the way down to skin and breath. Galaxies spin like slow weather, but the story lands in a heartbeat. Every atom in you carries a record of stellar work. Not a metaphor. Real reactions, real heat, real pressure. You hold a timeline that began in furnaces older than Earth, arranged today as organs, nerves, thought. The chain runs from collapsed cores and expanding shells to muscle and memory. Stardust is not a slogan, it is inventory. Carbon in your muscle fibers came from an old star's last gentle exhale. In late life, a star fuses helium into carbon and oxygen and then sheds its outer layers. That carbon drifts, cools, and joins clouds that later become solar systems. The oxygen you pull into your lungs formed during long main sequence cycles in hot, massive stars. The iron riding inside red blood cells formed when a star ended in collapse and explosion, thrown outward at thousands of kilometers per second. Those atoms are older than the rocks under your feet. Here is the unsettling part that becomes strangely calming once it sinks in. None of your atoms is younger than about 4.6 billion years. The elements did not assemble themselves fresh when Earth formed. They were recycled from older stars that lived and died in prior eras. Your body is a collection of veteran travelers. The steps that built those travelers follow a simple ladder. In ordinary, stable stars, hydrogen nuclei combine to form helium, releasing energy that holds the star up against its own weight. As cores heat and tighten with time, helium nuclei fuse to make carbon and oxygen. That is the easy part. Past that, energy yields fall. To push heavier elements together takes more heat and higher density. In the most massive stars, layers act like nested engines. Carbon burning, oxygen burning, neon and silicon burning, each at shorter timescales until the process reaches iron. Fusing iron does not pay back energy, it takes it. When a core turns to iron, the pressure support fails and gravity takes over. The result is sudden. The core collapses, outer layers slam inward and rebound, and a shock wave tears the star apart. In that brief, harsh moment, the temperatures and neutron densities shoot high enough to make elements heavier than iron. Some of that happens in the initial blast. More of it follows when matter streams through neutron-rich zones around the forming remnant. The ejecta mix into space, cool, and later seed new systems. That is one route to the periodic table. Another route waits in darkness for eons and then rewrites a region of space in a weekend. Two neutron stars orbit each other, radiate energy away, and slowly fall inward. At the end, their merger shakes space-time and launches a kilonova. In the first seconds, torrents of neutrons slam into atomic nuclei and build chains that jump far beyond iron. Gold, platinum, uranium. These events occur rarely compared to supernovae, but each one seeds large volumes. If a ring lies on a finger, its atoms likely crossed that kind of furnace. You can trace specific atoms back to families of stars. Calcium in bone forms in the fusion layers of massive stars and in explosive nucleosynthesis when those stars end. Sulfur in proteins shows up in the ashes of core collapse supernovae. Phosphorus in DNA comes from stellar interiors and shock-driven synthesis as material moves through the blast. The mix is not uniform. Different stars contribute different yields based on their masses and how their lives ended. The Milky Way is not just a city of stars. It is a chemical production line with distinct neighborhoods and shifts running at different tempi. Zoom out. Early on, the universe was simple. Mostly hydrogen, helium, and a trace of lithium. Complexity is an earned feature. Each generation of stars reworked the raw stock and returned enriched material to space. Massive stars went first, living short lives and exploding, rapidly increasing metallicity in young galaxies. Later generations formed from gas that already carried these extras. Our solar system formed from such processed material. The rocky nature of Earth depends on metals forged in long-vanished stars. No earlier generation, no continents, no tectonics to recycle nutrients, no stable climate windows long enough for life to test options. Even the way atoms bind inside you hints at their paths. Hemoglobin's iron sits at the center of a porphyrin ring, flipping oxidation states to shuttle oxygen. That single iron atom owes its existence to core collapse. Carbon's 4 bonds frame complex chains and rings because a red giant could hold its core quiet long enough to assemble stable carbon nuclei. Oxygen's role in cellular respiration mirrors its stellar abundance in massive stars that favored its production. Biology fits the tools the universe supplied because those tools were the ones available. Think about timing. The atom counts in your body encode a cosmic schedule. Hydrogen and helium are primordial. Carbon and oxygen joined later with the first big stars. Iron took explosions. Heavier than iron elements took rarer catastrophes. By the time the cloud that became the sun and its planets condensed, the inventory was stocked. That cloud inherited bits from many sources. Shells shed by elderly stars, supernova shock fronts, and the thin drifts of kilonova debris. The result was a disk rich enough to grow rocky worlds, volatiles, and organics. On that disk, dust grains carrying carbon, oxygen, and metals collided and stuck. Ice mantles formed around grains far from the young sun, trapping simple molecules. Repeated heating and cooling made complex organics. Small bodies accreted and then delivered those materials to the early Earth. Volcanoes vented gases. Oceans condensed. Chemistry ran in cycles, powered by sunlight from a stable star whose own core ran the basic hydrogen-to-helium reaction that first set this story in motion. Life borrowed old atoms and started keeping its own records in chains of phosphorus and carbon, adding nitrogen from earlier stellar cycles into bases that code for proteins. The spread of heavy elements across the galaxy shows its age and motion. Regions near recent star formation have higher metallicity. Older halo stars hold lower metallicity, preserving an earlier state of the universe's chemistry. Your atoms reflect a late-formed environment. They are the end of a long build, not the beginning, and they remain part of the flow. When you breathe out carbon dioxide, those carbon atoms re-enter cycles that reach plants, oceans, stone. In deep time, rivers and uplift return them to the air again. Nothing rests in one form for long on geological timescales. There is also a physical intimacy in this story that is easy to miss. When you press a hand to your chest, you are sensing a solution to the same balancing act that defines stellar life. Flows in, flows out. Pressure matched to keep structure from failing. Your body maintains gradients the way stars maintain support. When those gradients stop, structure falls to equilibrium and the pattern ends. The atoms remain, looking for new bonds and new roles, just as they did before they joined your life. This is not detachment from the cosmos. It is membership. You carry supernova debris diluted through clouds, mixed by shock waves, and welded into new molecules by sunlight and time. You breathe oxygen that once rode inside vast, hot stars. You write with a brain built from carbon that first cooled in a cloud illuminated by a dying giant. Gold if you wear it, condensed from the debris of a collision between remnants of dead stars. The oldest parts of you bear witness to eras no human watched. The line from stellar death to human presence runs through more than identity. Those same deaths built the scaffolding of structure on larger scales. Explosions drive shock fronts that compress nearby gas and start new rounds of star formation. Enrichment changes how clouds cool, which changes how they fragment, which sets the masses of new stars and the likelihood of planets. The chemistry that made you also shape the layout of galaxies, their colors, and their futures. Light from far away carries the record of these processes, but the evidence does not only arrive through telescopes, it circulates in your blood and rests in your bones, waiting for the next section of this story to show how stars draft the blueprints of the cosmos and keep rewriting them. Stars don't just sit in the dark and shine. They push. Ultraviolet light and fast winds shove gas aside, scooping out hollow cavities inside nebulae and sweeping dust into bright rims. Supernova shocks run ahead like plows, ramming into cold clouds and packing them tight until gravity takes over. New stars switch on in those compressed ridges. A single massive cluster can clear a hole dozens of light years wide, its rim glowing where radiation meets gas. What looks like a still photograph is machinery at work. Pressure, heat, and momentum rearranging the raw material of a galaxy. Astronomers call this chain of cause and effect stellar feedback. Young, hot stars flood their birth clouds with high-energy photons that strip electrons from atoms and heat the gas. Their winds carry momentum that adds to the pressure, and their end-of-life explosions stir the medium on even larger scales. The same stars that sweep their shelves clean also enrich what remains, loading it with heavier elements and dust. That mixture drifts, cools, and forms the seeds of planets in the next round. One generation changes the chemistry and structure for the next, so a galaxy keeps renewing itself through both constant erosion and constant enrichment. There's a catch, and entire galaxies lean into it. In a starburst, gas converts into stars at a frantic rate. Thousands of suns turn on within a few million years, packing dense regions with fierce light. These systems glow far above their usual brightness, radio to infrared to X-ray, but the price is steep. They chew through their gas fast. Winds and supernovae also punch channels that let material escape the galaxy entirely. The engine runs hot, then stalls. The lights dim because the fuel bill came due. That is the paradox. More output, less time. Not every system runs like that. Older galaxies can drift into a quiet phase where new stars form slowly, if at all. Their light skews red, not from dust, but because long-lived stars dominate the tally. You see rounded bulges with smooth light and halos where globular clusters hang in remote orbits. Those clusters are dense balls of ancient suns. They still circle the outskirts, their members older than the solar system. The contrast is stark. Violent birth in crowded cores versus patient aging under a calmer sky. To read a galaxy's past, astronomers study its mix of stars. Blue-white, high-mass stars do not live long, so if you see them, the region is young. Red giants tell you time has passed. They are evolved stars, swollen after long main-sequence lives. Variable stars polish the picture. Some of them, especially a certain class, reveal a link between how quickly they pulse and how bright they truly are. By tracking that rhythm and comparing it to what we detect, we can work out distance. This made it possible to reach beyond our own system of stars and map structures that lie far outside it. A simple pattern in a flicker became a ruler for space. Wind and blast do more than push gas around. They change what that gas is. Heavy elements do not exist in quantity in pristine clouds. They build up when stars synthesize them and then return them to space through winds or explosive endings. Over many cycles, the average metallicity rises. That word means all elements heavier than helium in astronomical language. With more metals come more ways to cool, because atoms and dust grains radiate heat away efficiently. Cooler gas collapses more readily, and the solids that later become rocks and cores of planets only appear once that chemical path opens. Each generation, the recipe grows more varied, and the outcomes get more complex. Textures in nebulae show this work. Shells expand from young clusters, layered like tree rings where shocks passed by at different times. Filaments stretch away from bright cavities, tracing magnetic fields that guide the flow. At the edges of bubbles, new stars cluster where compression overcame turbulence. The numbers can be large. A bubble can span tens of light years, and the ring around it can host hundreds of young objects. Seen in infrared, the cavities stand out as warm arcs, while ultraviolet carves sharp boundaries and emission lines. Even in quiet regions, a nearby supernova can arrive and flip the switch, compressing a dark zone into a nursery. On the scale of a whole galaxy, this adds up to weather. Hot bubbles merge into superbubbles, punching through the disk and venting into the halo. Some of the expelled gas cools and rains back down later. Some leaves for good. Star formation then becomes self-regulating. If it runs hard, feedback lifts gas away and slows the rate. If it slows, gas settles, cools, and the rate can rise again. But a sudden inflow of fresh material from a merger or a close pass with a neighbor can break the balance and spark a starburst. The pattern is not fixed. It responds to supply lines and to internal pressure. Where do we see the long view most clearly? In those ancient clusters on the outskirts and in the colors of a galaxy's starlight. We also see it in the way distances line up when we use variable stars with known behavior. The method revealed layers upon layers of structure out beyond the Milky Way. Each measurement carried a small uncertainty, but together they built a ladder that reached far. That, in turn, let other methods calibrate themselves. Once the scales stretched out, wider questions could be asked and checked. The point is simple. The properties of stars let us read the map. As time passes, the chemical story deepens. Winds from massive stars deliver carbon, nitrogen, and oxygen. Later, explosive events add a spread of heavier elements. That enrichment spreads unevenly at first, tied to the local history of activity. Mixing and time smooth it out. When new clouds condense from the enriched medium, solids form more easily, and protoplanetary disks gain enough heavy material to build rocky planets and complex molecules. The diversity of worlds owes its start to that slow build-up, one cycle after another, across billions of years. The path from a small change in brightness to a measure of distance might seem narrow, but the impact is broad. One observer carefully recorded how certain stars brightened and dimmed in a regular way, and found a strict relation connecting their period and intrinsic brightness. That relation became a tool used everywhere. With it, astronomers pinned down how far certain galaxies are, scaled the size of the local group, and established a base for more distant markers. The reach of the known universe widened because one detail in a specific class of stars turned out to be reliable across space. All of this returns to light, not only as energy, but as information. A photon records where it last scattered, what atom changed its path, and how fast its source is moving along our line of sight. When that photon passes a massive object, its path curves. The effect creates arcs, rings, and stretched images of remote sources. By studying those distortions, we learn how mass is arranged in between, even when much of that mass does not shine. Gravity writes a faint script across space, and starlight reads it out for us. This is why a nebula can look like a hollowed shell, why some galaxies blaze and then quiet, and why old clusters still keep watch in the dark halos. Stars act on their surroundings from birth to death, and the next generation responds to what the last one did. The glow we see across a galaxy is a census of ages and a record of pressure, motion, and chemistry. And within that glow, Every tiny change in brightness and shape carries a measurement we can use, a clue to where matter sits, and a path into deeper structure that the eye alone would miss. Einstein made a prediction that sounded like a trick of language. Mass bends space, and bent space bends light. If that is true, starlight doesn't move in straight lines. It follows curves, and those curves can split one distant source into several ghostly copies. A single star could appear in two places at once, straddling a foreground galaxy like a pair of mirages. Astronomers tested this by watching how light behaves near massive systems. We saw arcs, rings, and duplicated images that drifted with the gravity in front of them. The sky wasn't broken, it was warped. Gravity had become a lens. That lensing turns empty patches of sky into crowded archives. When we stare for weeks at a small square of darkness and let telescopes collect every last photon, thousands of faint galaxies climb out of the noise. The longer we look, the more ancient the light becomes. These photons left their homes billions of years ago and crossed expanding space to arrive now, one by one. Each one carries a small report, the color, brightness, and shape of a galaxy that no longer looks that way or may not even exist anymore. The present sky is layered with the past. The path light takes is not a clean arc. Space ripples around mass like water around stones. A galaxy cluster deflects starlight passing near it. The amount of bending depends on how much mass sits in that cluster and how the mass is arranged. If the alignment is right, the background galaxy gets stretched into a long arc and brightened. If it is perfect, the image wraps into a ring. More often, the lensing is subtle, just a gentle skew that requires careful statistics to measure. But even weak distortions add up. By mapping these shape changes across the sky, we infer where mass lies, including mass that emits no light. Natural magnification opens a door that our instruments alone cannot. Lensing boosts the brightness of galaxies that would otherwise be invisible, pushing our reach farther back in time. It has exposed compact star-forming regions, primitive galaxies, and at times, the light of a single distant star briefly sharpened by the lensing effect of a passing clump of matter. These events teach us not only about the distant sources, but also about the lenses themselves. The way the images split or smear reveals the mass distribution in the foreground. In this way, gravity writes a kind of cartography we can read. We lean on another tool when the universe provides its own controlled explosions. Type Ia supernovae are the outcome of a white dwarf pushed over a critical threshold in a binary system. The result is a thermonuclear flare that reaches a peak brightness with small variation. Because their intrinsic brightness is so consistent, we treat them as standard candles. Measure how bright one appears, and you can compute its distance. Combine that with the redshift of its host galaxy, and we learn how fast that part of space is receding. When astronomers gathered many of these explosions across wide stretches of distance, a pattern emerged. The most distant type Ia supernovae did not shine as brightly as expected for a universe that was slowing down under its own gravity. They appeared dimmer, which pointed to them being farther away than a simple decelerating model would allow. The expansion of space had sped up over time. We gave the driver of that acceleration a placeholder name, dark energy. It acts not like normal matter, but like a pressure locked into space itself, pushing galaxies apart faster and faster. This conclusion did not rely on a single event. It grew from dozens, then hundreds of careful measurements. Each supernova had to be tracked, its light curve recorded, and dust corrections applied. Selection effects had to be understood. Even after all that, different teams using different telescopes converged on the same trend. Space expands, and the rate of expansion increases. That discovery turned type Ia supernovae into more than distance markers. They became a probe of cosmic history. Meanwhile, the bending of light offers another way to test that history. Lensing depends on geometry. The positions of the source, lens, and observer determine how strong the effect will be. In a universe whose expansion changes over time, those distances stretch in specific ways. By measuring how often we see strong lensing, how thick the arcs are, and how weak lensing distorts vast fields of galaxies, we get an independent check on the expansion rate and how structure grew. The two methods, standard candles and gravitational lenses, cross-check each other. One looks for depth using known brightness, the other reads the fingerprints of gravity along the way. Every photon that reaches us brings fixed evidence. It has the energy imprinted at emission, red-shifted by expansion, nudged by gravitational wells it crossed, and sometimes multiplied by a lens. We can separate these clues using spectra. Absorption lines reveal which elements sit in a galaxy's gas. Their shift shows how fast space expanded while the photon traveled. The shape of a lensed arc tells us how mass is arranged in a cluster we can't weigh by light alone. These data sets overlap and reinforce one another, letting us build a coherent picture out of faint signals. There is a quiet discipline to this work. Observers keep pointing at the same field, integrating more light. Analysts remove foreground stars, calibrate detectors, and correct for instrumental drift. Modelers generate many possible mass distributions for a lens and compare them with the observed arcs until one solution fits. When a type Ia supernova appears in a survey, the clock starts. Early time spectra, peak brightness, decline, and host analysis all feed into the distance calculation. None of this happens with a single glance. It requires time, consistency, and care. The reward is not abstract. Lensing lets us map dark matter, a presence that doesn't shine but anchors galaxies and clusters. The distortions it leaves on background galaxies show where it lies. Standard candles reveal how the scale of the universe grows. Both tie into a larger narrative about structure and expansion. We learn how small clumps formed, merged into larger halos, and gathered gas that cooled into stars. We learn how the balance between gravity and the outward push of dark energy shaped the web we see today. When we say the universe is accelerating, we do not mean we feel it day to day. The effect reveals itself only across great distances. The light from distant supernovae carries that testimony. It had to cross a cosmos where the fabric stretched a little more with each passing billion years. That stretching dimmed the light more than gravity alone would account for. The dimness is not a flaw in the source. It is a statement about the space between. Gravitational lensing adds texture to that statement. In some cases, a single supernova is lensed into multiple images, each arriving at a different time because their paths through warped space differ in length. By timing those arrivals, we measure delays that depend on both the mass of the lens and the expansion rate. Light, bent and delayed, becomes a ruler and a clock. It allows us to check our distance ladder in yet another way. All of this rests on a simple fact. Light takes time to travel. The farther we look, the farther back we see. We do not need metaphors to call this time travel. It is built into the speed limit that light obeys. When photons finally reach our detectors, they tell us how stars formed in the past, how galaxies assembled, and how the expansion of space changed. That is why deep fields matter. They let us listen to faint voices that have been on their way to us since before Earth formed. So the next time a blank patch of sky fills the frame, keep watching. Arcs will show where hidden mass lies. A crisp flare may betray a standard candle marking out distance. Every photon carries a record of its route, bent by gravity, stretched by expansion, and preserved long enough for us to read it now, as we turn from how light travels through a curved universe toward the ripples that shake space itself. Two collapsed stars orbit each other so fast their paths blur into a single loop. Each lap bleeds energy from space-time itself. The orbit shrinks. The frequency rises. They whip around at a significant fraction of light speed and keep stealing momentum from the fabric they ride upon. This is not a quiet dance. It is an engine. It drags the grid of distances and times into a faint tide that passes through everything, including you. No telescope sees the approach. The universe feels it. When they finally touch, the violence hides in plain sight. Space stretches and squeezes in a narrow pulse that races across the cosmos. The wave front reaches Earth, and our detectors shift by less than the width of a proton, then settle. A short delay later, a new light climbs out of a distant galaxy. A kilonova, the glow of fresh matter formed in crushes of neutrons and heat. Gold and platinum condense out of neutron-rich debris and expand into interstellar night. Telescopes trace the chemical aftermath as the light cools from blue to red, the same way metal cools after forging. The signal fades in days, but the products last as long as planets. A neutron star is the collapsed core of a dead giant, but in these mergers, it becomes a process more than an object. The orbital energy converts into ripples in geometry. Nuclear crust peels back, inner layers mix. In that moment, matter becomes a factory for the heavy elements that normal stars cannot make. The gravitational waves carry away information about the masses, spins, and the stiffness of neutron matter. Light carries the chemical fingerprints of the R process. Put together, they outline both the crash and the metallurgy it triggers. The event ends in seconds. The evidence travels for millions of years. Some stellar ghosts remain solitary, but restless. Magnetars take the neutron star blueprint and add a magnetic field beyond ordinary physics. Their fields reach levels that wrench electron shells out of shape and twist their own crusts until it cracks. When that crust fails, a starquake produces a gamma-ray flare that crosses light years. The burst delivers more energy in a heartbeat than the sun will emit over hundreds of thousands of years. Earth's instruments catch these spikes as sudden saturations. Space agencies catalog them and triangulate their origins. The scale of the energy is not hype, it is measurement. The rarest outbursts come from a few known repeaters. Even their quieter phases distort the plasma around them. Charged particles in the magnetosphere accelerate along field lines and emit across a wide range of wavelengths. The geometry changes as the crust shifts, and so does the emission pattern. Some cycles run for years without an event, and then let loose with no warning. These systems are safe at their distances, but they demonstrate a limit case for matter. A magnetic field that's strong is not a metaphor. It exerts pressure that rivals gravity and reshapes the state of atoms. Other remnants find stability through speed. Pulsars are neutron stars with beams aligned just enough to sweep past Earth. They spin with a precision that rivals the best clocks humans have built. Millisecond pulsars reach more than 700 rotations every second. Their timing does not drift randomly. It follows the slow loss of rotational energy as magnetic radiation carries away momentum. Astronomers use arrays of these natural clocks to monitor the galaxy for very long gravitational waves, looking for correlations in the arrival times that would suggest the whole grid swelled and shrank together. The mechanism inside a pulsar looks simple and remains unforgiving. A magnetic axis offset from the spin axis turns the star into a lighthouse. Charged particles accelerate near the magnetic poles and emit radio waves, X-rays, or even visible light depending on the environment. Each rotation sends a pulse to anyone aligned with the beam. Tiny hiccups, called glitches, reveal shifts in the superfluid interior that adjusts its rotation in quantum steps. Those jumps tell us that even after death, a star can host states of matter that never occur in planets or in ordinary metal. Sometimes the end is slower and more luminous from a distance. When a star strays near a black hole, the difference in gravity across the star shreds it. The outer layers stretch into a thin, luminous stream. The inner debris winds into a hot disk that flares as friction and compression convert orbital energy into radiation. A tidal disruption event can outshine all the normal stars in a galaxy for a short burst, then fade over months. The light curve declines in a pattern controlled by the rate at which the black hole feeds on the remaining stream. Observatories monitor galaxy cores for these flares. Spectra show heated hydrogen, helium, and sometimes heavier elements as the gas orbits and falls. The emission lines broaden with speed, and models translate that width into a mass for the black hole. Because the star tears apart outside the event horizon, the process becomes a clean probe of gravity near the limit. The star vanishes, but its last light tells us about the landscape around a hole we cannot see directly. Each event refines our maps of galactic centers and the way they grow. These deaths and half-lives share a theme. Once a star collapses, it does not simply leave a rock behind. It becomes a machine with outputs we can detect across space. Mergers right in space-time itself. Magnetars broadcast the stress of their own exteriors. Pulsars keep time with better regularity than any human device in space. Tidal disruptions show us the slope of gravity near horizons. None of this light or motion suggests a clean finale. The remains continue to affect their surroundings, sometimes for longer than the original star shone. The 2017 observation of a neutron star merger showed both types of messengers at once. Gravitational waves that arrived first and a kilonova that followed. This combination confirmed that these collisions forge heavy elements and that the space-time ripples carry details about the matter inside. It gave a template for future searches and a way to coordinate detectors across the planet. Since then, surveys have flagged candidates that fit the same pattern, strengthening the case that a portion of the gold and platinum in our solar system came from such a collision long before the Sun formed. Magnetar flares arrive as brief spikes in detectors on satellites. A handful have been so strong they saturated instruments looking at the entire sky. Follow-up observations track the decay and look for changes in the star's spin or emission pattern. The energy involved does not require much time to release. It requires stress stored in the twisted field and the crust that resists it. When the crust yields, the sudden rearrangement dumps energy into radiation. The event warns that death in the stellar context can remain active long after the shell has fallen. Pulsars continue to add tools to physics. Their timing arrays test general relativity on large scales. When a pulsar orbits a companion, the system loses energy to gravitational radiation, and the orbit shrinks at a rate that matches predictions. Individual pulses can reveal plasma in the interstellar medium by dispersing differently at different frequencies. In compact binaries, a pulsar's beam can even heat the facing side of a small companion, stripping it over time. The same clockwork that alerts us to waves across the galaxy also sculpts the fate of nearby matter. Tidal disruption events help map feeding cycles at the centers of galaxies. After the peak, the fading follows a power law that tracks how quickly the black hole consumes the debris. Some events drive jets aligned with our line of sight, adding high-energy emission and complicating the spectrum. Others are quiet in radio, but bright in ultraviolet and X-ray. The differences trace the environment near the hole and the spin of the central object. Months later, the light withdraws and the core returns to its baseline glow, as if nothing happened. All of this leads toward a boundary where the usual carriers fail. Black holes hold regions where light cannot cross out to us. Information about what falls in seems to vanish from view. Yet gravity outside still reflects the mass and spin of what resides within. We watch the aftershocks and the edges. We read the sky by distortions and delays. Stellar ghosts shake the medium we live in and write their messages in waves and flares. From here, the path runs closer to the engines that drive these extremes and to the question of whether endings can seed beginnings we do not yet understand. A star strays too close to a supermassive black hole, and the rules change. Gravity doesn't swallow it in one bite. The pull stretches the star, first subtly and then violently, into a long stream of hot gas. Parts of the star speed up, other parts slow down, and the difference tears it apart. The debris forms a loop that swings around the black hole, collides with itself, and settles into a bright, tight disk. That disk heats to extreme temperatures and flares in X-rays and ultraviolet light. The brightness can rival a whole galaxy for a while, then fades as the remaining gas spirals inward. These tidal disruption events are rare, but when they happen, they light up the region around a black hole that otherwise hides behind darkness. Some stars survive near the edge of that danger. At the center of our Milky Way, a tight group of stars whip around Sagittarius A star at extraordinary speeds. One of them sweeps in close enough that light would take only hours to cross the distance between it and the black hole. At closest approach, it moves more than 5,000 kilometers per second. Astronomers watched its orbit bend in a way that matches predictions from general relativity. The light from the star reddens as it dips into deeper gravity, and the timing of its motion lets us weigh the black hole with impressive precision. The paradox is simple. These stars live in an environment where tidal forces shred the unwary, yet they keep orbiting for many cycles, giving us a clean laboratory for strong gravity. Near the event horizon, matter that doesn't fall straight in builds a traffic jam. Gas circles, heats and churns in the accretion disk. Magnetic fields twist and tighten. Under the right conditions, the system launches jets along the black hole's spin axis. These jets shoot out at speeds close to light and plow into surrounding gas. Where they strike clouds, they compress and heat the material. In some regions, that compression can help trigger the collapse of dense clumps, which leads to new stars. A dead or dying star that fed the black hole becomes part of the fuel that seeds the next generation. At larger scales in galaxies, this feedback shapes the flow of gas, clearing some areas and piling up material in others. Destruction and creation run on the same engine. Not every close pass ends in capture. In some encounters, a binary star system wanders near a supermassive black hole. Gravity pulls the pair apart in a few swift moments. One star gets trapped on a tight orbit or plunges inward. The other is thrown outward at such speed that it escapes the galaxy. These hypervelocity stars fly into the halo and beyond, carrying the story of their ejection with them. Their speeds are so high that no future orbit brings them back. They cross intergalactic space alone, still burning, even as their home galaxy falls behind. We detect a few of them in the Milky Way, their paths pointing away from the center, matching the idea that the central black hole can act like a slingshot. Everything that crosses the event horizon leaves no trace in light. That boundary marks the limit of what can be observed directly. For all practical purposes, information about the detailed state of matter that falls in does not return to the outside universe. Yet gravity keeps track of mass and spin. The black hole's pull, the shape of space-time around it, and the way nearby stars and gas move all reveal the presence of the hidden mass. We can map a black hole we cannot see by watching how it bends the behavior of everything nearby. In mergers of massive objects, the gravitational waves that ring down after collision also carry signatures that match horizons instead of surfaces. If a compact object lacked an event horizon, the waves would echo differently. So far, the signals we capture fit the black hole picture. The stars near Sagittarius refine that picture. Their orbits do more than confirm the mass. They also test how space distorts near a compact object. Small shifts in timing and spectral lines across each orbit match the way relativity says clocks and light behave in strong gravity. The fact that these stars still exist after many passes tells us their closest approaches, while extreme, don't cross the line where tides would rip them apart. The line is sharp. A slightly different path would have turned them into streams of gas and a brief flare. Instead, They keep circling, marking out coordinates for us in a place where everything else is chaos. Jets from actively feeding black holes reach much farther than their disks. They can stretch across thousands of light years, punching through interstellar gas and carving lobes of radio emission. In galaxy clusters, central black holes inflate cavities in the hot plasma that fills the space between galaxies. The energy they deliver slows cooling in the cluster core and changes where new stars can form. That link between a tiny horizon and a vast region of space helps set the growth rate of galaxies over time. The same process shapes the heavy element content of the gas that later condenses into stars and planets. The hand of the black hole writes at scales far beyond its size. Hypervelocity stars are a reminder that gravity's influence includes what it rejects. When we plot their paths and measure their chemical makeup, we can tell whether they formed in the disk and were later accelerated, or whether they carry a signature of the dense central regions. Their ages, spins, and compositions help reconstruct their origin stories. Each one is a fast-moving probe sent from the core into the dark between galaxies, where it may travel for billions of years without a close approach to another star. The event horizon sets a clean rule: what goes in stays in. Outside, the mass and spin remain, and the geometry that they impose affects orbits, gas flows, and the timing of flares. Inside, details are lost to us. This creates the tension at the edge of black hole physics. We model the inflow and the light that escapes before crossing the horizon. We watch the flares that rise and fade. We listen to the gravitational waves from mergers and compare the waveforms to theory. Each observation narrows what a black hole must be like, but the horizon itself stays beyond inspection. The universe keeps secrets behind that line while making their outlines obvious. Stars caught at this boundary between survival and destruction shift our sense of scale. One event can release more energy in a short time than many galaxies produce on average, yet that energy depends on a single unlucky star meeting a slope in space-time it cannot climb. A different star with a slightly larger pericenter distance will speed around and leave, altered but intact. A small change in conditions leads to a completely different outcome. That sensitivity defines the neighborhoods of black holes. Across cultures and centuries, people tracked the steady lights and moving wanderers of the sky for stories, calendars, and routes. They did not need to know about horizons and jets to find meaning there. Today, we read those same lights with instruments that turn small shifts in color and time into maps of invisible mass. We now know that some of the points in the sky skim past a darkness that hides everything it takes, and that some are flung away to loneliness by a gravitational transaction in a single pass. The physics adds detail, but the experience remains similar. We look up and find guidance in patterns we can trust, even as the truth behind them grows stranger. Those stars on tight orbits around our galactic center will keep circling for a long time. Their motion will continue to mark the outline of a black hole we can neither touch nor see directly. Sailors once steered by steady stars, farmers planned by seasonal risings, and storytellers tied lives to constellations. The same sky now shows us thresholds where existence thins, and where a star can be both witness and victim of gravity's steepest wells, leading us toward the older relationship between people and starlight that began long before anyone knew what a black hole was. The first nights were clean and loud with starlight. No cities, no engines, just ocean and sky repeating across the horizon. Canoes slipped off volcanic shores into open water, and the route across thousands of kilometers lived entirely in memory. Polynesian wayfinders learned the rising and setting points of key stars like a chant. They knew when Arcturus stood where the swell changed, when a faint band of the Milky Way tilted at a useful angle, when seabirds flew toward land at dawn and back to sea at dusk. Star paths ran like invisible highways stitched to the compass of the mind, and the sky served as a clock, a map, and a ledger. No written chart fixed to wood or stone could match a navigator who kept the whole dome of heaven in sequence. The names, colors, seasonal shifts, and the cross-checks with wind, wave texture, and cloud reflections that hinted at islands beyond the curve. Now hold the same sky at arm's length and notice the trick. The constellations that feel solid are lines we drew from one spot in space. Orion's stars sit at different distances, spread across light years, unrelated except for our angle of view. The Big Dipper looks tight because we stand here. Give those stars time and their slow drift bends the handle and scatters the bowl. The pattern is a snapshot. The sky keeps moving even when we don't notice. Cultures read these points in their own languages. Egyptian farmers watched for the heliacal rising of Sirius, its brief return to the dawn edge after invisibility, and prepared for the Nile to swell. The date anchored festivals and fields. Far from the river's silt, priest astronomers in Mesopotamian cities recorded planetary wanderings against the background of fixed stars. Their regularities and oddities became calendar tools, omens, and a framework for tracking years. Across deserts and coastlines elsewhere, constellations were not the same set of heroes and monsters familiar to modern star charts. Indigenous traditions named birds, fish, canoes, rivers, and ancestors. On some winter nights, the dark lanes of the Milky Way became the figures rather than the bright stars between them. The dome overhead held law, genealogy, and geography at once. Even the one point we treat as steady, north, slides over deep time. Earth's axis wobbles slowly, describing a circle in the sky across about 26,000 years. The title of pole star changes hands. Around 3000 BCE, observers could have pointed to Thuban in Draco for true north. Today, we use Polaris. In about 12,000 years, Vega will stand near that spot. Ancient builders aligned stone and brick to stars that no longer hold those bearings. Future navigators will steer by different anchors, and the same lessons will still apply. The reference is useful, not eternal. The oceans made these facts practical long before telescopes. On a black sea, the horizon removes distractions. Sailors used star heights above the water to track latitude long before they had the math to name it that way. They paired star lists with seasonal wind patterns and routes of migratory birds. Oral training preserved the syntax. This star rises here, sets there. When it reaches that height at dawn, turn this degree into the swells. A low band of cloud after midnight might glow faintly from unseen lagoons reflecting starlight. The knowledge rested in voice and repetition, not ink, and the accuracy supported families, trade, and survival. Meanwhile, the shapes you know are loosening. Proper motion, the slow drift of stars across the sky, barely shows up over a lifetime, but it adds up. Give it a few millennia, and Orion's belt will open. The Big Dipper's bowl will skew, and new patterns will occupy the same corridors of sky where old stories lived. None of this breaks the usefulness of the stars. It simply means each era draws its own lines. The maps are temporary. The method persists. Calendars once depended on a single star's brief return. Sirius, hidden in solar glare for weeks, reappeared just before sunrise and signaled an annual shift that mattered to fields. The timing guided floods, planting, and harvests. The star didn't cause the river to rise, but its schedule matched the river's pulse closely enough to set community rhythms. This is how a point of light becomes part of infrastructure. Not every culture carved the same night into the same units. Some saw a celestial palace, others a canoe, others a dog, and others a hunter. The interpretations came from land, animals, rivers, and work. Different climates and horizons pull different stories from the same dots. Where the air stays dry and clear for months, fainter stars join the language. Where clouds roll in, brighter stars carry more weight. But under all the differences, you find the same practice, tying memory to the sky so it can travel. The wobble of Earth's axis doesn't only change the pole star, it shifts where the sun rises against the backdrop of stars across long spans. Alignments in old temples drift out of exactness, even though the stones haven't moved a centimeter. This slow change is not a failure of design. It's a record of time itself passing at a scale most tools ignore. You live in a snapshot taken midway through a cycle you'll never see complete. People 5,000 years ago occupied a different snapshot. People 10,000 years from now will stand under yet another. Stand outside tonight and let your eyes adjust. The photons from bright stars left years ago. Some from faint galaxies left when early people chipped stone. The waves reach you after crossing distances you could sail against for a lifetime and never reduce by even a fraction. Those same streams of light guided a canoe into safe harbor, told a farmer when to dig a canal, laid out a city's avenues, and gave language to a song meant to be recited until the mouth knew it without thought. You and a sailor from 1,000 years past share the same tools: a horizon, a sky map, and the patience to keep them matched. The comfort in calling the Big Dipper by name sits beside the fact that it is changing as you say it. The stars have their own velocities and destinations, and the galaxy's mass steers them along wide curves. Over time, the familiar Dipper becomes something else. Some of its members belong to a moving group that travels together. Others don't, and that difference will show more clearly later. The pattern you learned as a child is a useful address for now, and that brings an easy truth to carry forward. Stars shaped routes, calendars, and myths. They granted direction on open water and a shared schedule on riverbanks. They still do those things in new forms. Yet the same lights carry their own change. They age, they shift. The grid humans laid on them bends with time. The next part of the story follows that motion because even the steadiest markers in our sky are part of a larger drift, and the constellations that feel like home are already on their way to becoming something we have not named. Stars seem nailed in place. We inherit constellations like street maps, and the sky looks the same year after year. But permanence here is an illusion caused by distance. Every star moves. Each carries a small drift across the background called proper motion. From a single lifetime it hides, but over long spans the canvas stretches. Lines we learned as children loosen, angles widen. The figures slip their frames. What looks fixed is slow motion too slow for our senses. Give that motion enough time and the effect becomes unmistakable. Over 10,000 years, the sky would look alive. You would notice the Big Dipper's handle bending backward as individual stars pull on their own routes. Cassiopeia's W would sag on one side. Orion's belt would no longer line up like pearls on a string. The slow shuffle becomes migration. Shapes dissolve because they were never real structures, only patterns made by perspective. Each star follows its own orbit around the galaxy, and no two orbits match in speed, tilt, or eccentricity. The geometry we project onto them cannot survive the drift. We are passengers too. The sun carries us on a long path around the Milky Way, a circuit that takes on the order of hundreds of millions of years. One lap is longer than the span from early mammals to us. While we ride, the neighborhood changes. Today's bright companions will slide away and new ones will rise, shifting the mix of familiar and unfamiliar points. The constellations visible from Earth do not just deform, their cast rotates. Species come and go over the course of a single galactic year, and so do the recognizable star patterns. Dinosaurs looked up at an arrangement that would not guide a modern navigator. Zoom in on how clusters dissolve and you can watch the mechanism. Open clusters form with hundreds or thousands of sibling stars packed into a region only a few light years across. They share age and chemistry, and at first they share direction, but they aren't tightly bound. galactic tides tug at them. Close passes between members trade momentum. Over hundreds of millions of years, the group thins. Some siblings fall inward toward the denser regions of the disk. Others drift up into the halo or lag behind and spread into streams so dilute they vanish to the eye. The night sky is full of former families, now scattered into anonymity. A few leave hints, subtle moving groups whose shared motion betrays a common origin, like the Hyades and their cousins drifting apart. Most trace a quiet exit, changing the sky star by star. The Big Dipper offers a neat example of this kind of hidden kinship. Several of its bright members belong to a moving group sliding together through space, but others are unrelated. That is why the cup and handle will warp at different rates. Parts of the shape hang together for a while, then the imposters peel away. Over the next 50,000 years, the classic ladle breaks into an awkward arc and a separate triangle. You can run the clock in either direction and see that the shape we learned is only a brief snapshot in a long rearrangement. Some of the most dramatic motion belongs to nearby, faint stars that slip sideways faster on the sky because they are close to us. If you watched carefully across decades with a telescope, you would see a few creep relative to background stars. Their shift proves the whole field is in flux. They show the general rule. The closer a star lies to us, and the faster it moves through space, the more obvious its proper motion becomes. Put that motion on a map and the heavens look like a flow field, arrows pointing everywhere, lengths set by speed. Scale up from neighborhoods to the full disk and the sun's path becomes a long, slow spiral around the galactic center. We drift through arms and between them. Dust lanes that block parts of the sky now will not be the same ones that obscure future horizons. As we cross different regions, nearby stars grow more or less numerous, and the Milky Way's band brightens or dims depending on how much material lies along our line of sight. Even the best star charts are provisional, tied to the era that produced them. Our orbit through the Milky Way has another consequence. Encounters, not head-on crashes, but close brushes that alter trajectories. A passing star can nudge comets in the Oort cloud or adjust the pace of a moving group. Over millions of years, small changes pile up. The sum of many minor encounters helps dismantle clusters and stir the disk. Gravity keeps accounts that run to long deadlines, and the sky's slow rearrangement is the interest we pay. Deep in time, the biggest redraw comes from outside our galaxy. The Milky Way and Andromeda move toward each other. 4 billion years from now, the first pass will lift tidal streams across the sky. Star rivers will arc from horizon to horizon. Our own band of the Milky Way will twist, swell, and tear into bridge-like structures made of stars and gas. The night will hold shapes without precedent in human culture, because no human culture has seen two large galaxies mid-merger. After several close passes, their central black holes will spiral together and coalesce, while the surrounding gas compresses and ignites rounds of star formation. Nebulae will glow in new regions where shocks compress clouds. For a while, the sky brightens with fresh blue clusters. Later, as gas depletes, the merged remnant settles into a quieter form, and the lighting dims. Across these phases, the constellations we named disappear completely. There is no Orion or Scorpius in a sky being rewritten by a galactic collision. Navigation anchors shift to nearer, evolving markers, bright supergiants that live short, or ancient clusters that survive the storm. Then they too move, fade, or split, and the habit of drawing lines between stars will follow the shifting canvas, redrawn by whatever minds are present to trace them. The longer view stretches beyond any merger. Massive stars burn out first, so as ages pass, the population skews red and faint. Red dwarfs last, and they set the tone of future nights. The sky sheds its blue-white points and keeps a low, steady glow from countless small suns. Patterns built from such faint lights would be larger and softer. the way a city looks when most of its bulbs have gone out and the rest run on dim power. Against that restrained background, motion keeps going. Even in a quiet universe, the drift never stops. Call each familiar a landmark if you like, but treat it as temporary. The North Star we use now is not the permanent pivot of the sky, and neither are the lines we trace to tell stories or find our way. Over centuries, update follows update. Over millennia, the old guides fade and replacements arrive. Over millions of years, the entire set of shapes turns over. Many eras from now, distant descendants would write new atlases with diagrams that we would not recognize. Thinking in this time scale is hard because our senses are tuned to human lives. But once you let the clock run faster in your mind, the movements coherently assemble. The galaxy becomes a slow current. Clusters feather into the stream. Nearby stars overtake and recede. The distant haze rotates. The sky behaves less like a museum and more like weather on a timescale that hides from us. It is a moving system we happen to sample in a short frame. So when we say the sky is unchanging, we are really pointing to our own short window. The patterns that feel anchored are arrangements that happen to exist now. They formed, they linger, and they will dissolve. That is not loss. It is the way a dynamic system expresses itself. Hold that thought as we step off the human timeline and into the wider arc. The constellations that helped sailors cross oceans and guided calendars through seasons are snapshots from a particular era of the galaxy's life. Even those trusted marks are already shifting. And ahead, the great meeting with Andromeda will write a sky of arcs and flares before it all dims into the long age of red embers. With that in view, we can walk toward deep time without surprise, ready to watch the last bright configurations loosen into memory as the universe slows and light thins. Billions of years have passed since the last massive star burned out. The sun is a white dwarf, cooling in the dark, an ember left over from a brighter age. Across our galaxy, only red dwarfs still shine. They are small, steady, and faint. The Milky Way no longer glows in blues and whites. It breathes in a low red hush, a quiet scattering of stubborn points holding back the dark. The arms that once blazed with clusters now drift under a thinner light. Star-forming clouds have thinned. The loudest days of the cosmos are over. What remains are patient fires, a long afterglow stretched across space. Time has changed scale. The clocks that once ticked in millions and billions now stretch into trillions. Red dwarfs sip their fuel with extreme care. They mix hydrogen through their entire volume. They waste very little. They do not inflate into giants early in life. They do not blow off thick shells. They keep most of their mass and burn close to the minimum rate needed to shine. Because of this, they define a new era. The universe today is older than every human word for age, and still, most red dwarfs are only getting started. They could outlast every memory written in rock, ice, or atom. When historians of physics say the future belongs to low-mass stars, this is what they mean. The future is not bright, it is long. Under these stars, worlds would not know a true day. Many planets close to red dwarfs lock their rotation, one hemisphere always facing the star. Permanent dawn sits along the terminator, a ring of twilight where temperatures stabilize. The red dwarf above would not blaze. It would glow. Its spectrum leans to the red and infrared, so plant life, if it evolves, might favor different pigments, tuning to longer wavelengths. Photosynthesis would run on a slower rhythm. Skies would arch in a muted hue. Flares can be strong on many red dwarfs, especially when they are young, but over immense time scales their activity calms. If any biosphere adapts, it might build its resilience around long intervals of quiet, punctuated by brief spikes of radiation. Oceans, ice layers, or thick atmospheres could help buffer those shocks. Life, if it persists, would learn patience because the star demands it. A red dwarf's interior tells the story of endurance. Smaller ones are fully convective. New hydrogen is constantly transported to where fusion happens, and helium gets stirred outward instead of building a heavy core early. That mixing is the secret of their longevity. The star does not develop the same kinds of internal boundaries that force larger stars into short, dramatic endings. Everything flows. The cost of that efficiency is low luminosity. They light only their neighborhood. Across the galaxy, the collective light of billions of these small stars creates a dim, steady backdrop, a faint red scaffolding holding the last strands of starlight in place. As ages pass, even these stars lean toward quiet. They will eventually exhaust hydrogen. Their cores will thicken with helium. They will contract modestly and warm. Some may pass through brief phases of altered output as their internal transport changes. Then each will settle into a white dwarf state. The transition is not the violent shedding of layers you learn from sun-like stars. It is the slow ending of a long, careful burn. In the white dwarf phase, the star shines without fusion, radiating stored heat from past nuclear fires. At first, it is hot and bright for its size, with a surface temperature greater than most stars. It cools by glowing, like iron fading in a forge. No new energy comes from the core. The temperature drops steadily through billions, then trillions of years. White dwarfs hold quantum pressure in their makeup. Electrons resist compression, providing support against gravity. This keeps the remnant from collapsing further, as long as it stays below a critical mass. The size is near that of Earth, yet the mass can be similar to the Sun's. The physics is stable and silent. Cooling proceeds with the discipline of a clock. Crystallization may occur in the interior as ions lock into lattice structures. The star becomes more ordered as it loses heat, a paradox that plays out because it radiates energy to the cold outside. Slowly, its glow sinks beneath detectability. A black dwarf is the endpoint of this path. It is still the same object, the same matter, but cold enough to emit no visible light. None exist yet. The universe is not old enough to have made even one. The time scale to reach that state runs beyond our current age by orders of magnitude. But in the long arithmetic of the future, every white dwarf crosses that boundary. When it does, a star becomes a fossil. The sky fills with relics that do not shine. This leads to a wider change in the character of the cosmos. If expansion continues, the raw material for star formation grows scarce and spread thin. The bright past was efficient at consuming gas, building stars, and seeding heavy elements. But efficiency has a carryover cost. Fewer dense pockets remain to ignite. Over longer spans, galaxies drift apart, their light redshifted into wavelengths our current instruments would not detect. Interactions that once triggered bursts of star formation grow rare. Structure still exists, but distance and time stretch it beyond easy influence. In such a universe, the process that powers stars fades not through a sudden stop, but through equilibrium. Energy differences even out. Temperatures fall. Entropy increases. This is not a single moment. It is a gradient across everything. Heat death is a phrase that sounds harsh. In practice, it is an easing. No more engines run, no gradients remain to push matter into reactions that release fresh light. The universe rests, extensive and quiet. Its contents still present, but unable to do much more than coast. Planets freeze. Moons sleep under ice. Black holes remain as deep wells. Dead stars persist as cold structures. There is a calm in this view. Not everything ends in fire. Most of it ends in silence. The last red dwarfs give way to small white embers. Those embers dim below sight. The map of local space becomes a set of objects that mark where stars once lived. Old star clusters disperse. Any surviving civilizations, if they exist, will have had to work with less and less energy, stretching resources across longer seasons than life has ever known on Earth. The pace of everything slows. When we say the far future belongs to red dwarfs, we also say we live at noon. Our era is bright. The night sky holds hot blue stars and steady suns. Star-forming regions still sculpt gas into knots and filaments. Supernovae still mark the deaths of massive stars with brief brilliance. We still see galaxies crowding the sky of deep exposures. We still measure distances with the light of events that echo across millions of parsecs. We still watch planets transit stars close enough for their atmospheres to cast faint signals. This is a rare window. It will not last. So, while red dwarfs write the long chapter, we read during the daylight. The universe around us is active. It teaches with contrast. Rapid lives of giant stars, slow lives of small ones, death that enriches, birth that depends on that enrichment, and a long tale of cooling where the story thins out to bare facts. Knowing where it goes does not darken the present. It clarifies it. We can see how unusual it is to sit under a sky where many kinds of stars shine at once. And that opens a quiet question that we will take with us. If this long fade is the end of the line, then the story resolves into stillness. But if there are pathways we have not yet learned to trace, if the engines of gravity and quantum fields have corners that feed back into beginnings, then the rest state may be less final than it looks. Either way, we stand here in the bright epoch, watching a universe crowded with suns, and turn toward the possibility that the last chapters might hide an unexpected door. Suppose the lights do go out forever. If every star cools to a black dwarf and every galaxy thins into a sparse fog, is that the last sentence of the story, or just the end of a chapter we don't yet understand? The question sits between physics and philosophy. Heat-death describes one path. Energy spreads so evenly that nothing new can happen. But laws that permit stars, atoms, and space-time might allow patterns larger than a single universe. The same instincts that traced stellar life cycles now push us to ask whether the cosmos itself has a life cycle, with phases we only glimpse through theory and mathematics rather than direct sight. One proposal steps in from the edge of expansion. If gravity's grip over the very largest scales could someday overcome the outward rush, the universe might slow, halt, and reverse. A contracting phase would compress diffuse matter back into a hotter, denser state. Temperatures would climb, not in isolated cores, but everywhere at once. Fusion, which once needed stars as containers, would require no vessels at all. Squeezed hard enough, the whole cosmos would enter conditions like those near the beginning, the pressure rewriting the rules that structure matter. In that scenario, the big crunch would not be a wall, but a doorway. A new expansion could follow, a reset that sends fresh radiation and matter streaming out. A rhythm measured not in seconds, but in aeons. That breathing pattern is not a fantasy of symmetry. It relies on how geometry, energy, and pressure evolve together. Expansion depends on the contents of the universe and on how those contents affect space-time. If dark energy changes over time, or if new fields turn repulsive effects into attractive ones at extreme densities, the sign could flip. In some cyclic models, entropy doesn't keep piling up without bound because each cycle dilutes old clutter or hides it behind new horizons. Other versions carry entropy forward, but stretch space so much that each new cycle begins effectively clean to observers inside it. The common theme is simple. The story may loop, but each loop writes new details like star formation, rewriting the chemistry of a galaxy after every generation. Another path starts where gravity crushes light. A black hole is a region where escape fails, but the mathematics near its center invite speculation. If what we call a singularity is not a final point, but a bridge to a new expanding region, then collapse becomes genesis. In these ideas, every high-mass star that collapses beyond neutron degeneracy doesn't just end. It seeds a child cosmos on the far side of its horizon. The parent universe sees mass vanish behind an event horizon, while beyond that veil, a separate space-time blossoms, insulated from the parent by causal separation. No signal returns, but a world could grow there, complete with its own expansion, particles, and laws. That leads to a startling possibility. Our own universe could sit inside the interior of some ancient collapse in a larger framework. The parameters we measure, particle masses, interaction strengths, the density of dark energy, might be inherited traits, shaped by the physics of gravitational collapse in that parent realm. If so, black holes become reproductive organs at cosmic scale. They would be the places where parameters get tested and transmitted. Stellar death would then play a role beyond recycling elements. It would propagate structure across generations of universes. Some researchers take the metaphor further and propose selection. Universes that produce abundant black holes spawn more offspring. If the constants of physics vary slightly from one newborn cosmos to the next, those that happen to favor long-lived stars, heavy element creation, and efficient paths to black hole formation would, over many generations, dominate the family tree. In that frame, parameters like the strength of gravity or the neutron-proton mass difference might be near values that maximize black hole production. Not because of intentional design, but because lineages that drift toward those values leave more descendants. The generational picture mirrors what we have seen within a single universe. Stars form, live and die, and those deaths enrich the next generation with heavier elements, enabling complex chemistry in rocky planets. Scale that up and a pattern emerges. Structures give rise to processes that enable new structures. A universe with parameters that permit stable atoms, nuclear fusion, and gravitational clustering builds galaxies and stars. Those stars create the black holes that carry information about their existence into the possibility of new space-time regions. The macro cycle echoes the microcycle, even if the mechanisms differ. Consider what age means in this landscape. In one star's life, we measure millions or billions of years. In galactic evolution, we stretch to tens of billions. In a cyclic universe, the relevant unit might be an era, separated by a bounce or by the birth of an entirely new space-time region behind a horizon. Each era would have its own timeline, yet the generational process would transcend any one timeline, much as biological evolution persists through births and deaths. The clock that matters would not be a single arrow, but the branching and looping of possibility. These ideas remain speculative because the key events hide behind horizons or occur at scales and energies we cannot touch. No telescope can peer past an event horizon to confirm a baby cosmos. No detector can rewind an entire expansion to test a bounce. We work with consistency, mathematical elegance, and indirect clues. For example, we can ask whether the constants we see do, in fact, sit near values that maximize black hole formation, given stellar physics. We can study how entropy behaves in models that claim to cycle and look for signatures in the cosmic microwave background that might betray a pre-inflationary heartbeat. We can test whether dark energy changes with time. Each step trims possibilities without claiming certainty. What matters for us is the stance these theories invite. Heat death looks like an ending. Cycles and baby universes say endings can act as thresholds. Even if our observable domain cools to darkness, the creative potential may shift elsewhere or elsewhen. And if physics allows transitions that reset conditions, then novelty is not a brief spark at the beginning. It can reappear across scales and epochs. The universe's creativity would not be a one-time event, but a property of the underlying laws. Now fold that back to the most local fact we carry. Our bodies hold elements forged in stars. Carbon crossed a red giant's envelope, oxygen formed in helium-burning shells. Iron condensed out of supernova debris and settled into a disk that became a planet. If stellar death writes the ingredients list for life, then the grander cycles, if they exist, would extend that logic outward. The materials and laws composing us could be descendants of earlier cosmic cycles, filtered through many layers of selection and transformation. Our existence would then stand as one line in a much longer family saga, not at the end of a sentence, but mid-paragraph. This reframes the sense of finality that heat-death carries. Entropy still levels differences. Black holes still evaporate on impossible timescales. White dwarfs still cool. Yet the larger view allows for renewal at the level of universes. We do not get a guarantee. We get permission to consider that creation may be a recurring feature instead of a single miracle. The details we cannot resolve do not erase the pattern we can trace. Structures arise, carry forward information, open new channels for complexity, and then hand the baton to whatever can come next. So the question we started with does not need a tidy answer. It needs an honest one. If cycles exist, then existence is not a straight road into quiet. It's a landscape of valleys and passes, with threads that wind back into the sunlight by routes we cannot yet map. And if our universe is a branch on a much larger tree, then the silence that follows our last stars may be less an ending than a pause before a voice begins again in a different room. We have walked from the furnace of dying suns to the thought that whole universes may die and be born. Let's bring that scale down to something closer. There is a night, and there is a person lying awake under it, breathing air that stars made, hearing a quiet that connects to distances no map can show. Lie still for a moment and follow the quiet rhythm inside your chest. Each breath carries oxygen that began as ash in a star. Each heartbeat moves iron that cooled from a furnace older than Earth. The carbon woven through your cells once drifted through the outer layers of a dying giant, released into space and gathered up again by a young planet that would one day carry your name, your memories, your voice. Atomic history flows through your bloodstream with every pulse. It is not poetry, it is chemistry with a past. That past balances on a delicate edge. Your heart holds pressure like a miniature core, pushing blood outward while vessels and tissues restrain it, keeping form the way gravity and fusion hold a star in shape. You convert oxygen into energy and shed heat into the air, a steady exchange that mirrors the way a star turns mass into light and then leaks that energy to space. A small change in that balance alters everything. Too little oxygen and cells fail. Too much pressure and vessels strain. Life persists because feedback loops keep you near a narrow range, just as a star survives when outward energy meets inward pull. What starts as hydrogen and gravity in space has an echo in muscle, blood, and breath. The link runs deeper than metaphor. The calcium that hardens your bones formed in massive stars during later fusion stages, then traveled outward in stellar winds and supernova debris. Phosphorus, a backbone of DNA and ATP, needs neutron-rich environments to build up. Certain supernova conditions provide those neutrons, allowing the element to form and later seed star-forming clouds. The ring on a finger carries atoms like gold that likely arose during neutron-star mergers, where tidal forces and extreme densities drive rapid neutron capture before ejecta cools into heavy elements. These are not distant curiosities. They sit in your skeleton, power your cells, and rest in your jewelry. Your body holds a layered timestamp. The oldest atoms inside you formed billions of years before the solar system. Hydrogen in your water dates back to the early universe. Carbon, oxygen, nitrogen, sodium, magnesium, silicon, sulfur, and iron came from multiple generations of stars. Each carries a different production route and a different moment of release into space. Iron needed catastrophic endings when a massive star's core collapse drove shock waves that scattered heavy nuclei. Oxygen and silicon grew in the high-temperature shells of short-lived giants. Carbon emerged earlier, in stars that swelled and shed mass gently. You carry a mixed archive of stellar neighborhoods and lifetimes. You live at an unusual time in the universe. The night sky still holds countless bright stars. Galaxies remain busy with star formation, and heavy elements cycle through clouds into new systems. Red dwarfs dominate in number, but they do not yet dominate the light. This era will not last. In trillions of years, the night will favor dim embers. Right now, blue-white stars still burn, star clusters still sparkle, and nebulae still glow. You are alive during one of the brightest chapters. That context matters. It means telescopes can still read fresh starlight. It means planets like Earth still form from rich material, and chemistry stays diverse. Your daily daylight is a rare event on a long cosmic timeline. This is not an abstract privilege. It shows up in practical details. Photosynthesis uses sunlight from a stable yellow star that sits in a quiet part of a spiral galaxy. Our atmosphere holds oxygen produced by biology, but that chemistry only works because earlier stars seeded the planet with the elements needed for cells. Hemoglobin binds oxygen because iron atoms at its center can shift electrons between states just enough to catch and release. Those electron levels follow from atomic structure, and atomic structure follows from how nuclei formed. Even the tiny phosphate groups that shuttle energy in your cells depend on stellar nucleosynthesis pathways that supplied phosphorus early in solar system history. Stop and consider how many stellar events had to align for a single breath to work. Think about the water in a glass. Hydrogen from primordial times meets oxygen from massive star fusion. That bond cools and condenses into oceans and clouds. Every swallow includes atoms that circled the galaxy many times before Earth formed, mixed by shocks from ancient supernovae, and shaped by radiation fields that cleared and sculpted birthplace clouds. You run on that history all day without noticing it. You sleep with it moving through your veins. Your brain, which makes meaning out of this, also rests on atomic inheritance. Nerve signals move with sodium and potassium, elements with abundances set by stellar output and supernova enrichment. Myelin depends on cholesterol and proteins whose atoms trace back to the same supply chain of cosmic debris. Even the electrical activity of thought depends on calcium inflow at synapses, a resource built in stellar cores and delivered across interstellar space long before any nervous systems existed. Consciousness rides on a supply chain that began in star factories. This is a good time to notice how narrow your personal thermodynamic window is. Your body warms itself by turning chemical potential into heat and work, then sheds waste heat into an environment cool enough to accept it. A star does the same in a different regime. Energy flows from a hot interior outward to a cold cosmos. The second law sets the direction. Order builds locally, cells maintain structure, organisms learn and adapt, only because the larger system moves toward higher entropy. You sit in that stream. Your awareness is a small island surrounded by a wide energy gradient flowing from sun to earth to space. That gradient exists because nuclear fusion in stellar cores sustains it. The night keeps running while you sleep. Far away, red dwarfs keep their slow burn with convective cores that stretch fuel across their entire volume, extending lifetimes to scales beyond language. Neutron stars spin and sweep beams in regular pulses. Their timing drifts as they lose energy through waves and radiation, but they keep the beat longer than empires. Star clusters orbit, tidal streams peel off, and interstellar clouds shift under pressure differences and magnetic fields. On scales you cannot feel, galaxies continue their slow dance. On scales you can, your ribcage rises and falls, and the same physics that governs stars governs your breath. You carry no memory of those former stars, and yet their record is tangible. Meteorites show isotope ratios that track different supernova contributions. Ocean chemistry traces the balance of elements delivered to Earth. Your blood levels of iron depend on diet and biology, but the availability of iron as a planetary resource depends on earlier stellar deaths. Even the tectonic activity that cycles carbon through air and rock owes its materials to stellar outputs. You stand at the end of many chains that began as starlight trapped in elements. So when you lie down and the world goes quiet, you are not stepping away from the cosmos. You are returning to it. The atoms in your body do not belong to you for long. They pass through, just as they passed through clouds and stars before you. You are a temporary shape taken by ancient matter while the wider universe continues its work. That is not a loss. It is a connection you already live. Let your breath settle. The stars will continue. Small red suns will keep their steady glow for timescales that erase our calendars. Neutron stars will tick on, black holes will feed and fade, and galaxies will drift as their light thins into the background. You will sleep, and while you do, a trillion processes beyond your awareness will proceed, precise and indifferent, yet necessary for the next dawn. In this moment, you are conscious stardust. You are the part of the universe able to look back through time and follow your own atoms to their origins. That awareness is not separate from nature. It is nature finding context. Rest in that thought for a while. Out there, the long cycles continue, and in here, your quiet heartbeat keeps time with a universe that never stops.